please join me in welcoming our speaker this evening, Professor Alain Goriely.
Thank you all for coming. Thank you, Richard, and thank you to all my friends online. So today, as chapter 5, I will be talking about a rather difficult topic, a rather serious topic. It's difficult from an emotional point of view, but also from a scientific and mathematical point of view. And I have to say it's also a very personal topic, as it is something that I've been thinking and working for the last 10 years or so. And most of the results I will show you today are the result of that reflection with my colleague, collaborator, and student. And I will take you step by step on how we took the problem of dementia and try to understand it from a mathematical perspective and what we can get out of that reflection. So let me start with patient 0 in some sense. Auguste Detter, in 1890s, when she was in her 50s, she started showing some troubling symptoms. She has loss of memory, delusion, temporary vegetative state. She would have trouble sleeping and dragging sheet across the house and scream for hours in the middle of the night. She was admitted to the Herrenschloss, the Castle of the Insane in Frankfurt, a psychiatric hospital in 1901. Where she was around 50, and she was treated by Alois Alzheimer. And in exchange for treatment, she agreed to give all a medical record and a brain for scientific study. And we have excellent records of her condition as she deteriorated very quickly. All conversation were noted and so on. And she's the one who said in describing her own condition that she was losing herself. Eventually, in 1906, she died, and Alzheimer received a call from Frankfurt saying that the patient died, and they were sending a brain and all the medical record to him. He used the best at the time scientific technique, new staining techniques to study the brain and look at what was going wrong. And what is discovered is that the brain had two types of elements that couldn't be seen in healthy brain. There were two types of aggregate little clumps that we know now are protein clumps, the typical what is known as amyloid beta, and we'll talk more about it, forming plaques, and long fiber-like structure called tau, neurofibrillary tangles. These are the hallmark of the disease that we call now Alzheimer's disease, is the scientific definition of the disease, the presence of these two proteins at the time of death. And they are key to understand what's going on. So, amyloid beta is the first one, or the most important that's recognized. It is a plaque of a protein that we're not quite sure what its normal function is. It takes this form of plaque outside, it's an extracellular aggregate, where the tau tangle, we know, are there to stabilize the axons, stabilize neurons. They cross-link microtubule within this long structure to make sure to preserve their integrity. And sometimes they can form this fibrillary tangle, the aggregate, intracellular within the cell. This is Alzheimer's disease. This is what you see in the brain. If you look at the number, they're rather bleak. But as I'll show you later, there's now a little bit more of optimism at the horizon. Alzheimer's disease is the most prevalent form of dementia, accounting for about 60–70% of all forms of dementia. It's also the UK leading cause of death today, with 1 out of 3 persons over the age of 85 being subject or has some form of dementia. There are about 55 million people suffering in the world from these, not only them, but all the surrounding. And that number is known to grow very quickly, not as an epidemic. There's nothing to do. It's not an epidemic. It's not even exponential increase. It's just due to the fact that population are aging. We are better at curing and treating other disease, so people are aging and they are suffering more and more from these forms of disease which are related more to old age. It's also huge cost, estimated to go to somewhere around 3 trillion. But much more than the number is really the human toll. Let me go back to a particular case that I find particularly interesting. All such cases are heartbreaking. It's the case of William Utter Mullen. He was born in Philadelphia in 1933 and he studied at the Pennsylvania Academy of Fine Arts, but then moved to England in 1957 to study at the Ruskin School of Art in Oxford, before settling in London. His early work is characterized by linear expression with frequent inclusion of pop imagery and style. Very strong color use, and see here self-portrait that he made in 1967. But in his late 50s, he had some troubling sign. He could not tie his necktie, could not do the house finance, he had some memory problem. Maybe it was depression. Went to his doctor, and after a series of tests, he was diagnosed with what was called at the time probable Alzheimer's disease. The actual description of what Alzheimer's disease has changed. At the time, it was always probable until death and pathology. And that was at the age of 61. But with his wife, who was an art critic, he decided to keep a record of himself and his evolving condition by drawing self-portraits. And you can see the evolution of the disease as he paints himself, and as Auguste Deterdes is losing himself. This one is 96, early in the disease. You can see this full control of the color, of perspective, of himself. But rapidly, 97, 98, 99, and his last painting in 2000. And you can see really the loss of both fine motor control, the loss of visual impression, visual organization, all associated with problems related to the parietal lobe. He died a few years later in 2007. So this evolution of the disease is very personal to every patient. But if you look globally, it's actually quite regular. And this staging, this evolution of the disease is well recorded. Eva and Eiko Bragg, two scientists, have looked at the brain of different people at different stages of the disease, and they saw a very systematic evolution of the disease within the brain. And they describe different stages corresponding to different toxic level of protein in the brain, but also cognitive problem. Early on, stage 1 and 2, there is very little. What you see in this little circle are tau protein aggregate that have been properly stained. And it's there close to the hippocampi. And there's very little cognitive effect. Maybe people have problem orientating themselves. Maybe they have problem with episodic memory or problem with retrieving new memories. But by stage 3 and 4, things move quite rapidly, as we'll see. The problem with aphasia, word-finding difficulty that would eventually lead to anomia, global language loss, apraxia, inability to perform purposeful movement despite the fact that all the motor function are intact, agnosia, the inability to recognize objects or face, anosognosia, which is even worse in a way, it's the inability to recognize your own cognitive changes. By stage 4 and 5, as you can see, all the cortical area, the area on the outside of the brain, have been invaded by the disease. And there you have apathy, last period of vegetative state, agitation, irritability, aggression, akinesia, the loss of voluntary movement, irritation. It starts looking like Parkinson tremor, and then autonomic failure, incontinence, swallowing problem, blood pressure instability, leading eventually to death. Here is another picture of this progression, this spatial-temporal progression of the disease, here indicated in blue. Typically, Alzheimer's disease starts in the entorhinal cortex, close to the brain stem, and move to the hippocampi, and then invade the frontal lobe, and eventually all the part of the brain. So this systematic invasion is typical, that specific one is typical to Alzheimer, but if you take a broader perspective, you'll see that different neurodegenerative diseases have also this type of progression. Slightly different, they're related to a different type of protein, but overall follow the same type of systematic invasion. For instance, Parkinson's disease is related to another protein called alpha-synuclein, which also stabilizes axons, and starts within the brainstem and invades systematically the brain also with a given patterns, also recorded by the BRAC and BRAC. ALS, amyotrophic lateral sclerosis, is very fast. Is associated with another type of protein, the TDP43, that also make this clump and aggregate that kill neuronal cell and start the motor cortex, as you can see, and rapidly invade the frontal lobe and other part of the brain. That's the spatiotemporal progression of the disease within the brain, and we're going to try to understand that. But there is also a very clear physical effect on the brain. And that physical effect you can see here. On the left, you have the brain of somebody who was healthy at the time of death. You see that nice, round, well-formed brain, no problem. And on the right, you see the atrophy related to the loss of cell of Alzheimer. Right? It's walnut-like. It's all damaged. And if you look closely on a coronal slice, for instance, you can really see the difference between the two. And the typical feature that can be found, for instance, on an MRI that the doctor would look like, would be the larger ventricles, the opening of the sulci. Instead of being nice and round, you have this sulci opening due to the loss of cells, the thinning of the cortex, and the shrinking of the hippocampi. So you have real physical effect change in the brain. Right? The way doctors or the medical profession see the evolution of the disease is well captured by this curve. They call Jack's curve. Dr. Jack is one of the authority, and everybody in every single review in medical journal refer to a form of this curve called the Jack's curve. What do you see on the vertical axis are the biomarker abnormalities, and on the horizontal axis is time. A biomarker is anything that you can actually measure that is somewhat related to the evolution of the disease. For instance, in the red curve, you see amyloid beta amyloid. That's typically that you can extract from the blood or CSF. And it's the first one, it has a certain detection threshold, is the first one that will be seen in any kind of test that you give. Then you get to the blue one, which is the CSF-TO, cerebrospinal fluid, the second type of protein. It's harder to detect, so it's going to only appear later in the disease. Then you might see atrophy on the MRI, and you might see also some form of cognitive disease. So if you look for the disease, this little sign, atrophy, change in protein concentration, could in principle be seen before people really exhibit cognitive problem. So when I got interested in this topic, I read the literature and I found this curve, and I said, that's great. There is curve, so people have a mathematical model. I can go and understand what they've been doing. And then, of course, I discovered that there is no model. These curves are a way for doctors to synthesize their understanding. They're drawing on the page of what they think the disease is. It's not data, it's not an equation, it's just a drawing. It's a way to synthesize a basic ID. It's another way to express what I just told you. Disease starts slow, increase, and saturate in this biomarker, and so on. And so the next question was, is it possible to start from the basic mechanism of our understanding and actually understand derived curves like that and match them to the data? So this is the question and the challenges for us tonight. The first one, for somebody like me, a mathematician interested in pattern formation in various fields, morphogenesis and all that, I really wanted to understand spatiotemporal progression of the disease. How does that take place in space and time. So can I reproduce this pattern based on simpler mechanisms that describe the disease? And if I do that, can I then compute the atrophy that the brain experiences? And now, can I actually make a real mathematical model of biomarker evolution, and can I relate that to cognitive decline? So this was the challenge, and I want to bring you to the ideas of how you go about doing that. But before you do that, of course, the question is, why would you do that? First, I was told that this is the most complicated disease. There is no cure, no treatment at the time, nothing. This is way outside the realm of mathematics. Well, Daniel Bernoulli in the 1760s would disagree. At the time, smallpox was a problem, and he went to the academies, done some computation about probability and all that, and he said in very eloquent terms, why you use mathematics? He said, well, I simply wish that in the matter which so closely concern the well-being of the human race, no decision shall be made without all the knowledge which a little analysis and calculation can provide. So if the stakes are so high, why don't you just take the time and do actually numbers and compute things and try to relate exactly what is it? It's cheap, it's not particularly difficult compared to all human trial, experimentation, and it doesn't hurt anybody, as far as I know. But also, mathematics also allows you to understand the mechanism behind the disease. And Lewis Thomas was very also eloquent about explaining what are the general principle of disease, says it's necessary to know a great deal about the underlying mechanism before one can really act effectively. If you really want to solve the problem of Alzheimer, it's not just about trying drugs after drugs to see which one works. It's really to understand at the most fundamental and basic level. So the stakes are very high, but it's also an intellectually fascinating problem, putting it all together. So what are the mechanisms behind the disease? Well, at the same time, again, 10 years ago, Walker and Euchre is one of our collaborators, came up with the idea that all these different diseases, like Parkinson, Alzheimer, and others, all these protein-related diseases, are all related to some form of the same mechanism that they call prion-like by analogy to prion disease that are also related to proteins. And the idea is the following, is that you have these proteins that normally, in healthy case, are just of one typical form. But for some reason, it might be a random event or it might just be noise, that healthy protein misfold and take another shape. And that shape is somewhat toxic. And in which way is it toxic? Well, it's toxic because that new protein, when it meets a healthy protein, transforms it also into a bad protein. So the analogy that I like is that this is zombie apocalypse. The blue one is the healthy person, and for some reason, fungus, whatever, it transforms into a zombie. A zombie, when they meet somebody, they attack them, and the next person also becomes a zombie. Next thing you know, they go in little clump of group, attack everyone, and they aggregate in larger group, and sometimes they fragment. The little group divide and go to other place. That's what happened to this protein. They start forming aggregate, and some others go around and explore the city, do more damage. And that goes on until they form larger and larger group. They form protofibril in the case of protein, then fibrils, and then eventually these large aggregate neurofibrillary tangles. And just like in the movie, it ends, it never ends well for humankind or for the brain in this type. So the same process of autocatalytic enhancement takes place with this protein. One protein creates one bad protein, meet a good one, transform it, expand that population. The two cannot do the same, and so on, and so on, and so on. Okay? So that's just in words. What are the models that we have? So we have to simplify. We really have to take the important part. The important part is that you have a healthy one, in blue again, and a misfolded one. Then they can get together, form what's called a heterodimer, because there are two different ones, blue and red. And the heterodimer, because of chemical reaction between the two, turns the blue one into a red one. And then you have a homodimer, same of the same. And then they can fragment and make two new ones, and that process can go on. Okay? So if you just look at the start and the end, you start with blue and red, and you end up with two red. With that, you can write the reaction that it is. That's called the tilde, the one that are toxic. So you have P plus P tilde, blue plus red, so healthy plus misfolded, healthy plus toxic, is transformed at a rate K12 to two red ones, P tilde plus P tilde. That's simplification number one, and you can extract that. Okay? And now we can turn that into a mathematical model. So for people who were here last time, I said, don't worry about equation. Any model has three different ways of looking at that. The graphics, the picture I show you, so that you can visualize, the words, the explanation, and then to have a rigorous form, the actual mathematical equation. In this case, this model can be translated into mathematical equation that I can read to you. It says the change in time of the concentration of healthy and toxic protein is due to a number of factors. They can be transported, they can move around the brain, that's the first term. Don't worry about the particular form of what these mean. The important is that things can change by moving around. Your zombie can explore the city. That's all it means. Then there is a production of healthy particle, because in normal term, particles are always clear and recycled within the brain. That's part of normal healthy function. And they clear. The clearance also affects the toxic one. And you can transform, you can convert a healthy to a toxic one. That's the green part. Okay? So it's exactly what I told you, but not put in equation for which we can actually simulate and see what's actually going on by this interaction. But before we do that, we have a number of parameters, and at the moment we know nothing. We have too many things we don't know, so we want to simplify a little bit. And we know that in normal condition, the population of healthy protein is much larger than the toxic one. And if you use that, and you do a little bit of mathematics, you further simplify to a single equation where C is really the concentration of the toxic protein that has been rescaled with 0 and 1. 0 healthy, 1 toxic, right? So that's what we're trying to understand. So this new equation is a well-known equation within mathematics, was first proposed by Fisher in 1937, also by Kolmogorov in the Russian, and other people. In biology, in mathematical biology, is one of the most important equations. It shows how gene population evolve in space and time, or population dynamics evolve in space. It works for a lot of things. In mathematics, it's a nonlinear parabolic equation, and it's, despite simplicity, despite the fact that you can write with a few symbols, extremely complicated. We know there is no exact solution, and mathematicians have been studying and writing book for almost 100 years now about it. But still, it has all the physical mechanism and element that we need for our problem. It has this increase, that's this term, that tells you that if I forget about transport, the rate of change of the population is going to grow. It's going to grow, and just because I'm used to it, I know it's going to grow exponentially initially with exponential the alpha parameter. This is what happens when you have autocatalytic enhancement. You have this exponential increase, but the increase can only go so far, so you have a saturation term saying essentially when you reach a limit, you cannot go further. If you transform everybody to a toxic protein, there is no more fish in the sea for the zombies. Okay, I haven't told you about transport, which also turns out to be very important in our case. And in transport, we have something called anisotropic diffusion. Isotropic means things are transported the same way in all possible directions of space. But this is not what happens in the brain, and we know that. We have very nice experiment where in blue you see actually these protein aggregate to aggregate that are within the cell, and we know that they're transported much faster along the axon than outside the axon. So this is what you would have. You have very fast transport along the axon, but then for outside the axon, you need exocytosis and endocytosis for something to go outside the cell and be taken by a cell. It also happens, but in a much slower way. Okay, so fast transport along the axon. Think of the zombie always liking the big streets. These are your axon with that analogy. I don't know how long I'll be able to keep that analogy, but keep that in mind. So let's start as usual. When we don't know anything, we simplify everything. Says, how does this equation behave in one dimension? So I just look at one dimension, and I have on the vertical axis the concentration. And I start, I don't know if you can see there, at the bottom, at x equals 0, very little, tiny little bit of toxic protein. Very, almost nothing. And what happens if you let the equation run, if you simulate it, if you put it on the computer, it increases to 1 and then move and invade, these are called front, invasion front, the whole thing. Just like a lake would freeze and have a front of ice and water, you have that invasion. And we can relate directly the velocity of this front. You can do that mathematically rigorously. It was already known both by Fisher and Kolmogorov, that the asymptotic velocity of this front is related to the two parameters in the system. Rho, that's related to how fast things diffuse, and alpha, that's related to how fast the population expands. Okay, but that's just the warm-up. That's the homework exercise. The real problem is to do it in 3 dimensions. So the equation we have the equation that we started, that's the model, but an equation like that, a partial differential equation, you need a little bit more if you want to actually see what's going on. What do you need? Well, you need a domain. Where does the equation live? And the domain, in our case, is the brain. Call it B for brain or body. Mathematically, that means that C is a function of space and time, that for all x in the body and for time positive. That's just the mathematical formulation. You need boundary condition. Essentially, you said nothing lives through the boundary. So if I look at the normal through the boundary, I would say that the flux is 0 in that direction. Again, don't worry about the mathematical part. All I'm showing is that these words are easy to translate into symbols. And finally, you need to tell me where the disease starts. You need initial data. So you need to give me the function at time t equals 0 where it starts. And if you give me all that, then I can start simulating the process and see what happens. But of course, we have the equation, we need a brain. If I only had a brain. Okay, but we do have plenty of brain. And for people who've been here in chapter 2, my second lecture, I show how we can, from MRI, transform a brain into a mathematical representation, geometrical representation. Here is my friend and collaborator on this project, Ellen Cool in Stanford, and we put her in the MRI there on that day, and we zap her brain, zip, 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 the form, and then you put all that into a model, a 3-dimensional representation of the brain. And here it is. You see the gray matter, the cortical area. We have the skull, we have the cerebellum. Let's do that again. So what you see here is the gray matter. On top of that, with another color, is the cortical area. The green part is the cerebellum at the back. And then you have the skull, right? So what we have is within the computer, a whole brain model that has about 400,000 tetrahedral elements for the 3D representation. But you can also we also have 2D grids that we can do a faster simulation. So the brain is the first thing, but we also need the direction of the axon, because the transport is much faster in the axon. And this time we put Johannes in the scanner. And Johannes was a postdoc at the time, and now he's professor in Oxford and works on brain trauma and aging. So here is Johannes' map of axon. It's a vector field, meaning that at every point within that brain, we have a little direction where the axon point. And that means that if we have a little bit of concentration right there, it's going to go faster in that direction, right? So we have the domain, we have the brain with the direction of the axon. Now we need to know where the disease starts, the initial data. Boundary is easy, nothing leaves. So initial data, you can extract that from the literature of what is known. And what we started, very naively, we said, well, at some part of the disease, it's well established that amyloid beta is quite uniform within the brain, but that the tau inclusion typically starts close to that part of the brain, close to the entorhinal cortex. And that's all we did. And then we run the equation, and this is the result. So on the left, what you see is the evolution over time, and on the right is the infestation at mid-stage. Right? So let's go again. In red, blue is good, red is bad, as you can guess. And that shows you how much toxic protein there is at every point in the brain. Okay, so you can actually go and simulate that transport. How does it compare? Well, now you can look not only at amyloid and tau, but you can also do the same for alpha-synuclein, the TDP. They just have different initial data. We didn't make any other assumption about the basic of the mechanism. We said it's going to progress along the same equation, just with different initial data. And what we found was very striking, a big surprise. Because usually when you try things, it typically doesn't work first, and you have to understand. But here, systematically, we essentially had the entire progression of the disease from this very simple model, right? We could predict all the different stages and all that from this. Not only that, but we could also create the biomarker curve, the same one from Jack, so looking at how much overall protein, toxic protein mass there is in the brain at a given time. He is on a spread of 30 years. And what you see is amyloid being first, just like he said, and the blue curve is the tau, and the two other simulations correspond to two other diseases. So you recover also these now Jack's curve that are coming out of a model directly from the basic mechanism. Not only that, but you can now go back to the concentration level and couple that to a damage model that will tell you how matter is removed at every point depending on the amount of local damage, depending on the toxic protein. And you can map that to known scans of brain. And here's a brain that within 3 to 4 years went from that, here's the simulation, what you see is the increase in the ventricle, the opening of the Sulci, and so on, all the way to that point. Right? So you can actually look and predict the physical effect of that. So it was a good surprise, but rather than, okay, you're happy for a second, but then it naturally prompts the question, why does it work? Why would a simple model like that actually work and allows us really to understand and match, at least qualitatively, and even a bit more, match what is actually seen from clinical data? And so I only thought that what really is important for the brain is its topological structure, or things are related because these axons are the place where the transport is taking, and the fact that one region is infected before another one is really depend on how these regions are connected. So we wanted to go further and further explore that by simplifying the model really to the most important feature, which is that internal topology. And so we will look at network, and as Martin Luther King Jr. said, we are all caught in an inescapable network of mutuality. Whatever affects one directly affects all indirectly. So we want to understand how the evolution of the disease depends on the underlying topological structure of the brain. That was the next iteration in trying to understand what was going on. So in lecture 3, in lecture 4, I explained how we can extract a network from the brain, and you're welcome to go back. Let me give you the short version of that. You can look at different regions of interest in the brain. Here in this plot, there are 1,015 different regions in the brain, and see are they connected to other regions. So if I have two regions called I and J, I can look at all the connections that go between I and J and create this representation of the brain, which has nodes, so these are the region, and edges, which are the axon bundle connecting different parts of the brain, the connection within the brain. And I remind you also that we can extract very easily this type of structure and encode it into a matrix. Here is my simple example with 6 nodes. You see it as a given structure, much simpler than the brain, of course, but it's for you to understand. I can create a matrix A, the adjacency matrix. If 1 and 2 is connected, then row 1, column 2, and row 2, column 1, I have a 1 and a 0 otherwise. You see that 1 is not connected to 6, so I have a 0 in row 1, column 6. And I can do that for all the other ones. And very quickly, I can go from the graph of the network that you see on the left to a full representation by a matrix on the right, which, of course, computers like the representation in terms of matrix rather than drawings. If you do it for that big one that I show you, we had like 418 connectome data and we averaged them. And here's the average representative brain. And it's also weighted by the importance of the connection. And again, you can see the structure of the brain, that the right hemisphere, these blocks, is much more connected to itself than the left hemisphere. There's very little connection between the two, except through the corpus callosum in between the two brain or two hemispheres separated. And you see that directly just by looking at the matrix. Okay, I told you all about connectome in chapter 3. I hope you did your homework. Because now we're going one step further. And that step is, we have a connectome, we want to see how things can be transported on a network, right? If I put a little bit of dye there and it follows the rule that I give you, that it can expand and be transported, I want to know how it carries through the network, or I go from here to the different place. I want to understand that evolution. In order to do that, I'll have to do one more mathematical transformation. I'll take my adjacency matrix, the one that we just created, and I transform it into what is called the graph Laplacian. And it's very easy. The rule is very easy. You see that wherever I have 1, I'll have a -1. Okay, you can change sign. 1, -1. We all agree. And then on the diagonal, I just count how many 1s I have. I have 1 plus 1 is 2. Okay, let's see if we can do the next one. 1 is transformed into -1. 1 is transformed in -1. 1 is transformed in -1. I have 3 1, so I put a 3 in the diagonal. And doing so, I create a new object, transform object, which is central not only to a lot of process of transport, but is also one of the most important element of objects for people studying graph and network in pure mathematics. The advantage for us is that this Laplacian is a discrete form of the diffusion of the heat operator that we use in the previous model. That means that I can create a little system of differential equation that will predict how things diffuse just based on that matrix. Essentially, all you have to know is if I have that matrix, I can tell you how things evolve on a graph by themselves, just by diffusion. If you think heating one part of the graph, if it's made of brass and all big steel balls, you will see how the heat diffuse in different parts. It's all be governed by this one matrix and this system of equation. And now I can look at a new model that's essentially the same as the previous one, but only exists on that network. It has the growth, the alpha again, it has saturation, and it has this new transport term. So again, and it exists on each edge of the graph. So let me give you a very simple example. Simplest example has 2 nodes related to 2. And I start with here, I start with a little drop of toxic protein, and it has to follow the rule. So I just simulate that. And what happens is that initially, what we expect, initially that population is going to expand and slowly diffuse to the other node. And once the other node is seeded, it's going to increase also. Okay? So these are you zombie taking a plane to a different city before we know they're infected. And then the next city, the same thing happen. And you can follow that explicitly. Population expand, go to the other node, expand. And you can compute very easily the toxic concentration and the change. So now we have a continuous model that's defined at all points. It's a partial differential equation, very complicated object, very hard to simulate. And we have a discrete model, which only defines each node. It's an ordinary differential equation, which turns out to be remarkably easier to deal with and compute. A difference is for the one on the left, you need essentially a supercomputer or a big cluster, and you have to run it a couple of days in order to see what's going on. And the one on the right, you can essentially run it on your watch or your phone, right? So within a few minutes, you can see the evolution. So we have the clinical data, we have the continuum model, and now we have a discrete model. And Travis Thompson, who was a postdoc in my group, developed a program in order to easily simulate and visualize that. And now Travis Thompson is a faculty in Texas. And here is what happens now on the model, on the discrete model, starting at the entorhinal cortex, these two regions here, you have a little bit of infection, and soon enough, as you see, as you expect, it's going to propagate through the entire brain. You see the parietal temporal lobe being infected, and then going to the entire brain. The visualization is actually the part that takes most of the time. The actual evolution of the equation is very easy. So now we can go back to Bragg staging, remember this different step, and see more quantitatively if we can reproduce this pattern. And that was the work of Pramaputra, who came from Indonesia to do his PhD with me, and is back there. He's also a faculty there. And what he did is systematically study this type of system, both on the computer, but also from a mathematical perspective. And what you see, I don't know if you can see it, is dotted line, approximate solution, actual mathematical formula that he derived in order to approximate the solution, in order to get more insight. And what you see is interesting is that if you have a certain detection threshold, and this different curve correspond to the different area of the Bragg staging, so initially, you'll have this initial phase against the entorhinal cortex with very little. And what he shows is that you always have a period, which I call the denial period, where there is very nothing, no activity. But what happens is that the disease is being spread everywhere, and that's before you can see it. Okay, there are zombies in plenty of different cities, but you don't see much activity yet. And the different staging, 1, 2, 3, 4, 5, 6, are naturally recovered by the model. And that really tells you that this model takes as a main component the topology of the connectome, and that these staging are related to the connection in the brain. That's a really one to do. Okay, but that's all still very, very theoretical. And as Edward Deming said, without data, you're just another person with an opinion. So the next step, which was very hard and took us years, was really to try to pin down getting good data. And until a few years ago, we didn't have good enough data, but data is being generated all the time, in order to really characterize finally the model and be able to make actual prediction on the evolution based on this model, network model that I told you. The data that we use is called tau-PET data, positron emission tomography. And the idea is that you can inject a tau tracer and tease a certain molecule that binds into the tau proteins and that you can do imaging from. And what you see here, stage 0 is a healthy adolescent, actually, and stage 1 to stage 2 to stage 3 to stage 4 is the evolution of the disease, right, in longitudinal study. And so you see, as it goes from blue to red again, the systematic evolution for the different stage of the disease all the way to the last BRAC staging. We use ADNI, it's the Alzheimer Disease Network Initiative, that is a public database, and BioFinder 2, which is from our partner Oskar Hansson in Sweden, which we collaborate. They have a big initiative. And we identify within that whole data set 119 and 141 different data points that we could actually use for analysis. And the work was done by Pavan Shagar, who finished his PhD last year with me. The paper that I'm going to tell you about actually was accepted last week. He now works with Oskar Hansson at Lund University and keeps working in further developing this model, and we still collaborate together. And so what he did, he says, well, I'm going to look for a model that not only characterizes these, but also takes into account the heterogeneity of different regions. Different regions have different cellular composition, and the level of tau protein is not the same at each point. And so we have a model with 168 parameters that he managed to fully characterize. And the evolution of the disease then within his model, again, it's an iteration of the model I show you, but not that different, show you again the evolution of the protein within the disease. And how good is it? It's actually extremely good. So on the vertical axis is our prediction based on the data once we fit all the parameters, and on the horizontal axis is the actual data point. So if you have perfect match, everything would be on the axis. But when things are so clustered, that means you have very high correlation. So our predictions are actually extraordinarily good. And these we only took people with scans that either have 2, 3, or 4 scans. There are not so many, but this is what we get. But much more than that, not only a model can be calibrated, you can actually do individual prediction. And this is the overall load for a given person. And the 3 circles that you see are the data that we use, and the 2 squares are the data that we don't use and that match the curve. So with the 3 first points, we obtain the whole trajectories. So typically the scan are taken between either 6 months or a year. With 3 points, we can map the entire trajectory. We don't have the other one because data is still coming and we don't have people with 5, 6, 7 scans yet. But we predict with it that 95% interval, the evolution. Not only we do it at the global level, at the individual level, so for a particular person, personalized prediction, but you can also do it at the regional level. Not only say, oh, it evolved within the entire brain, but in every single region of the brain, we can predict that. And why is that prediction important? It's particularly important for drug trial because you want to know the trajectory of the disease so you can best identify the cohort that you want to try a trial for. So that's the main. Prediction, in a way, I show you, the BRAC staging always lead to the somewhat same evolution of the disease. So knowing that fact is not that, of course it's important, but it's not something that helps you change it, knowing the trajectory. But knowing the mechanism that leads to the disease and that there are different trajectories, different subtype of Alzheimer's disease, and probably different type of treatment for each one, that's important. So you need to know how things evolve in time. But prediction is not all. As Richard Hamming says, the purpose of computing is insight, not numbers. Okay, and so as a last few examples I show you of the work that we've been doing, let me tell you how we see what do we do with this model in order to gain that insight. One of the work is from Andrew Ahern, who is still doing his PhD and just published a paper on that. And that's to model cerebrovascular pathology, or the actual blood vessel interact with the disease. And why is that important? But for one thing, as Alzheimer progress, it also damages blood vessels, it reduces clearance within the brain and makes things even worse. So you want to understand that feedback. But you can also look at the other way, that you can have injuries, trauma, stroke, and all that, that would locally damage the vasculature. And by locally damaging the vasculature, it prevents the normal clearance of all this toxic protein. In order to do that, we have another type of model at a different level that actually characterizes the blood vasculature of the capillaries that tells us how this reduces the inflow and the outflow within that region and hence reduce clearance within the brain. And with that knowledge, you can identify which parameters are either going to lead to going back to the healthy state or turn into severe pathology, like in this case. Right? So now we can start not only understanding the evolution of the disease, but also it's related to other aspects of the physiology. Vasculature is completely different than anything I've told you, but these are also very important, for instance, for vascular dementia that is intimately related to the vasculature. And of course, people ask me, what about treatment? Can we help? And this is where there is a little bit of hope. When I started 10 years ago, there was no cure, no treatment. Everything had failed. There was maybe some help, some palliative cares that were applied. But things have changed, and very quickly, especially over the last 5 years. It's much better understanding, new biomarker, new connection with immune treatment, new connection with various aspects of the vaccine and so on. And a few years ago, new drugs. The first one by Biogen was aducanumab. It's not being used anymore. It's been taken out of the market. It's been replaced by Biogen also by lecanemab and by Eli Lilly donanemab. MAB at the end is for monoclonal antibodies. These are immune therapy. And essentially, they have the form there, the molecule that I show you at the top. And what they do is that they are a form of antibodies, and they can go and attach, they're designed to have affinity with a version of the amyloid beta plaque, not the tau. Right now, there is no tau therapy, even though tau is more correlated with damage, but amyloid is always in the picture. And it attached to these amyloid oligomers, and the immune cell, the clearance mechanism, are going to remove them from the body. Right? And now there are two drugs that not only have shown efficacy in lowering the amount of amyloid beta in the brain, but also, in a modest way, improve cognitive scoring of the patient, about 20, 30%, something like that. And so that gives a lot of hope, because now we have something that's effective and that actually is proven to do something. So, another part, we wanted to understand how the different time scale of treatment are connected to how good or efficient a given treatment is. And that was the work of Georgia Brennan, who finished a PhD also last year, and is now working with GlaxoSmithKline and in Oxford, and we still work together on developing further pharmacokinetic model. And that's a paper that also was accepted recently, a couple of months ago, where she looks at the effect of different type of treatment. And just to give you an idea of what you can do with mathematical modeling, here is a plot, and let me explain to you. The two axes are how much drug you give, how much milligram of a given drug you give, and on the how often you give them, so the interval between each treatment. And the black curve that you see, the Cmax, are the maximal toxicity for a given drug. You can only give so much before it does certain damage. So for the purpose of this discussion here, let's assume that Cmax for a given drug, one of the two before, is 400. And you give donanemab that's given every 4 weeks. That means that you can only give so much dose right at this intersection, right? That's how much. After that, it's too toxic. If you go more dose or more often, it's too toxic. So that limits there. But what this analysis shows you, that's the dosage, right? The dose and its time interval, its frequency. what is, and the color gives you the value of how much plaque it removes. Now, you can play a simple game. It says, suppose that I can change my time interval and I want to remove as much plaque, so I want the same color. How can I do that? Can I improve? And the answer is yes, you can follow a line that on that line you remove the same amount of plaque by changing the time interval to 2 weeks, like lecanemab is every 2 weeks, and by having a lower dose, 20. So you can give 20 whatever units every 2 weeks rather than 60 every 4 weeks and reduce the toxicity in the process for the same effect. Okay. This is very academic case, but it tells you the power of these ideas. It's not something you can just extract randomly from data. You really have to understand the underlying mechanism in order to be able to do something to that nature, very precise. So let me conclude. Remember all the different challenges that we had, trying to understand staging, trying to define atrophy and the biomarker. I show you now that we've made some progress in understanding spatial-temporal invasion of the disease. We can compute also the atrophy of in the process, and we can obtain the evolution of these biomarkers naturally and implement them, map them to data, and implement and ask questions about the system. Or is it related to other disease? Or is it related to other physiology? And so on. And which I didn't have time to talk about, we have also modeled that couple the effect of Alzheimer's disease to the actual cognitive state, see how the activity of the brain change as the disease progresses. And now we're trying to pull all the data of amyloid beta, tau, and atrophy, all the data together within a single model that explain all these aspects. To conclude, let me end up with reflection. This is a painting from Hieronymus Bosch, more than 500 years ago, 1494, one of my favorite paintings. And what you see here is interesting. It's called the stone of folly. A doctor is trying to extract the folly, dementia, from the brain that people thought maybe early version of a amyloid beta plaque, something like that. But what strikes me in the picture are the different characters involved. And so you have to ask yourself, who are you in the picture? Are you the patient who's so desperate for any relief that would believe the doctor? Are you the woman on the right, the public, who believes in anything that they hear, that blueberry cures Alzheimer, or in her case, that knowledge can be gained by putting a book on the head? Are you the spiritual leader who seems to be a little bit inclined in drinking too much? Or the scientist and the doctor on the left, which is also a little bit sketchy, you know, with his funnel on the head. Would you believe that guy? Or maybe we are little bits of everyone in this picture. Thank you.